Alright, so 7.4 nuclear fission. Here we go. At the start of this course, I promised that you would get to use the equation E equals mc squared. Well, consider that promise delivered now. E equals mc squared. That's the mass energy equation. And of course, this is Einstein's equation, famous physicist. And in this case, c, the letter c here, is the speed of light. Which is 3.0 times 10 to the 8 meters per second. That's how fast light moves in a vacuum. Now, it can slow down if it's going through other materials. Okay, E equals mc squared. That's the name of the game here. E is energy, m is the mass, and c is the speed of light. Okay, the mass of what? The energy of what? We're going to see. This equation is going to go with our law of conservation of mass energy. You might remember earlier we had the law of conservation of energy. We said energy can't be created or destroyed. And then I said, actually, that's not quite true. It isn't quite true because energy can be converted into mass, and vice versa. So what we really have is that the law of conservation of mass energy says that mass can transform into energy and energy into mass. The total mass energy in a system where mass energy is sort of this combined quantity in a closed system is conserved. Which means that you can't create any more or destroy any more. And that is true. The last one I said it's not quite true. This one is true. And this is what we're working with in this lesson, is that equation and that law of conservation of mass energy. So to work with this, we need to know some details. We need to know how heavy protons and neutrons and electrons are. We need to know their mass. And so we have their mass here. There's a table, and we have the mass in kilograms, and then the mass in these atomic units, U. And so the atomic mass unit, to the right here, 1 U is equal to 1.66 times 10 to the negative 27 kilograms. And that's the conversion there, and it just becomes a useful conversion so that we can talk about protons and neutrons, and they're right around 1 unit. And electrons are a bit less, of course. A fair bit less. Electrons weigh a lot less. Okay, and another useful measurement that we have here is a mega electron volt. This is just a measure of energy, like a joule. It's just a different unit, and it's based off of the number of volts that an electron carries. So 1 mega electron volt, MeV, like this, is equal to 1.602 times 10 to the negative 13 joules. Okay, that's our conversion there. So this is information we're going to need. We've got a bit more information that we need. The mass defect and the binding energy. So what these are, mass defect. What I'm going to tell you right now is that in the nucleus, let's say we have 2 protons and 2 neutrons in the nucleus. So let's say we have helium. Now, if I was to add up 2 protons and 2 neutrons, well, I could take the mass of 2 protons and the mass of 2 neutrons, add them up, and I could see how much the nucleus should weigh. And what happens is that that number, how much it should weigh, is actually larger than how much it actually does weigh. And what's happened is some of that mass of the protons and the neutrons has been converted into energy. It's true. If you take a helium nucleus it weighs less than how much it should weigh. It weighs less than just adding up the protons and the neutrons. So some of the mass of the protons and neutrons has actually disappeared. And that's called the mass defect. This is the difference between the calculated mass of a nucleus and its actual mass. This is the mass defect. Now, another important thing here is binding energy. So this mass defect, the mass is disappearing, it's being converted into binding energy. The binding energy is what holds the nucleus together. And so it is the amount of energy needed to separate a nucleus. That's the binding energy. So the nucleus is actually held together, and we need to use some energy to separate them out again. And that's going to end up converting that energy back into mass. So, without any further ado, let's try calculating this. Let's see what the story is here. It says determine the mass defect and the binding energy of a lithium-7 nucleus, given that its actual atomic mass is 7.01600 units, and using the particle mass table above. So, let's see. And actually, I want to make one correction above here. I said the difference between the calculated mass of a nucleus, I meant actually of an atom. Of an atom. Nucleus is not correct because we actually do need to include the electrons as well. Okay, so we'll go back down here. We've got a lithium-7 nucleus, so we've got 3, 7 lithium. Well, that has 3 protons, and it has 4 neutrons, and it has 3 electrons. Okay, so I want to calculate how much that should weigh. If I add all those together, what should I get? This is equal to 3 times the mass of a proton, 1.007, 276, plus 4 times the mass of a neutron, 1.008665, plus 3 times the mass of an electron, which is 0.000549. And notice I've used atomic units for all of this. Atomic mass units. That's okay. It's going to work out for us. So I get 7.058135. I'm keeping lots of extra digits here because we're going to need them. We get very, like the small little decimal places matter a lot in these questions. So our mass defect, this is delta M. I'm actually just going to go ahead and write that in here. Mass defect is delta M, the change in the mass. Okay, so delta M, the change in mass, the difference between the actual and the expected. Well, we expect there to be 7.05818.135. And what there actually is, the problem tells us that the actual mass is 7.01600. So that difference in mass is 0.042135 units. That's our mass defect. Good. Now we get to use E equals mc squared. I'm actually going to write delta mc squared, because that's how much mass we're changing into energy. That's what the equation means. We're taking a certain amount of mass, in this case our mass defect, we're converting it all into energy. And that's how much energy we're going to get, mc squared. Okay, so we have our delta M, 0.042135 0.2135, and we multiply that by c squared. So 3.0 times 10 to the 8, and we square that. And I need to do one last thing here. I've been using atomic units, so I need to make sure I convert those atomic units into kilograms. 1.66 times 10 to the negative 27. That's our kilograms per unit. Okay, that resolves my equation so that I can be working in kilograms. That's very important. So this gives me 6.29 times 10 to the negative 12 joules. And that's my final answer. So that's my that's my binding energy. My mass defect was above. The question asked for those two things. And we're going to do one more thing. I'm going to write my binding energy in terms of mega electron volts, because that is, in nuclear physics, a good way to write things. So 6.29 times 10 to the negative 12 times, we've got 1 mega electron volt over 1.602 times 10 to the negative 13 joules. So this gives me 39 mega electron volts. That's how much energy is produced. Or that's the binding energy. So that's how much the nucleus is being held together. That's the energy there. So we're going to see that that's actually, we can get that energy back if we're able to split the atom apart, which is what nuclear fission is all about. The topic here is nuclear fission. If we can split the atom apart, we can get some of that energy back. And that's how we make a nuclear bomb. That's how we make a nuclear fuel reactor. We're splitting the atom and getting some of that energy back, the binding energy. Okay. So on that topic, nuclear fuel. You can see a picture here to the right. We've got uranium. We've got a neutron firing towards that uranium, and what happens is that neutron absorbs that uranium takes in the neutron, and then it says, oh, hang on, I don't know how to deal with this. It splits apart, and what it does is it creates 3 neutrons and 2 daughter atoms. And those daughter atoms, here we've got barium and krypton, but it's not always going to be those two. But this is an example here. So you can see the equation, U-235 fission. We've got uranium plus a neutron, goes down to krypton, barium, and 3 neutrons. These two things here, it's not always going to be those elements. It's going to be 2 daughter atoms where the protons need to add up to 92, which is uranium. All right, and what's important when we have some sort of nuclear fission reaction is we want to create a chain reaction in a nuclear reactor. And a chain reaction is a repeated series of reactions where the products of a reaction create a new reaction. And you can see how this picture here would be a chain reaction, because this reaction produces 3 neutrons, and each of those neutrons can go find another uranium and make it split apart, which is going to create 3 more and 3 more, and it's going to actually build so that you keep on getting more and more neutrons out of this, which will cause the fission reaction. All right, on the next page here, we'll just say there are some other nuclear fuels that are used. Uranium is one of the big ones. So uranium-235 was the example on the previous page. And I just want to say there's a couple others that are used. For example, a big one is plutonium. And particularly it's plutonium-239 is a very good nuclear fuel. So that's what's used in the States. They enrich plutonium. Okay, another one that's good, creates a lot of reactions, is thorium 232. And one last good one is another type of uranium, uranium-233. Those are all good fission fuels. All right, so we're going to do one more problem about this mass defect and binding energy. We're going to say, what is the energy yield of this fission reaction using the given masses below? So we've got a reaction, and we're going to see the mass defect because we can say we can find the mass on one side, on the left side, and the mass on the right side, and you'll see that our mass is less on the right, which means that we've actually converted some of that mass into energy. So let's just give that a shot. Let's see what happens here. So what we have on the left, I can say here mu. Let's see. How do I want to say this? Yeah, we'll say on our left is mu, the mass of uranium, plus the mass of a neutron, because we've got one neutron on the left. And we can say that that is going to be equal to the mass of our cesium plus the mass of our rubidium plus 3 times the mass of a neutron plus some mass defect, some delta M. Okay? And this delta M is what's sort of disappearing, the mass that's being changed into energy. So if I want to find my delta M, my mass defect, I can say delta M is equal to the mass of the uranium, so all the mass on the left side, this is the mass on the left, minus the mass on the right. The mass of the cesium plus the mass of the rubidium plus the 3 mass of the neutron. This is my mass defect. I can plug in all my numbers now. It tells me the mass of uranium. I've got 235.044 plus the mass of a neutron. We have 1.009 minus, let's see, the mass of our cesium, 139.909 minus 92.922 minus 3 times our 1.009. Okay, this should give us our mass defect. And it comes out to 0.195 atomic units. Now, if I want to convert that, I probably want to convert that into kilograms. So we've got 0.195 times 1.66 times 10 to the negative 27. And this is kilograms per unit. This gives us 3.237 times 10 to the negative 28 kilograms. That's our mass defect. That's how much mass we are converting into energy now. So we can say E is equal to delta M C squared. We can find out our energy here. We've got 3.237 times 10 to the negative 28 times our C squared, which is 3.00 times 10 to the 8 squared. And this equals 2.913 times 10 to the negative 11 joules. And again, it's always good form to write this in the end in mega electron volts. So we would do our conversion there. The conversion gives us 181.9 mega electron volts. There we go. That's how much energy we get out. Cool. So one last thing here, this is just a bit of more information as opposed to math, but this is about Candu reactors. I mentioned in an earlier lesson that Canada has some pretty special nuclear reactors. They are different than the American form. Most of the world uses the American reactors, and that's mostly because the United States are very good at selling themselves and going to third world countries or going to places that need the technology and convincing them that they should buy the American technology. But in reality, the Canadian technology is it's more affordable, it's safer, it's more efficient, it's in all ways actually vastly superior to the one that's used in most of the world. And one of the reasons that it's not used more around the world is that it produces as a byproduct, it produces plutonium. You use uranium, you use actually unrefined uranium, which is very easy to get as natural uranium. You use natural uranium and the reaction actually ends up producing weapons-grade plutonium. And the United States doesn't want all these different countries around the world to be able to make their own weapons-grade plutonium, so they don't like people using Candu reactors. So there are a number of reasons why they're not more common. But they are incredibly safe. They're way safer than the American system, and it's really a shame that they're not used more. So here's a bit of information about Candu reactors. There's a picture on the right here of sort of how they work. And I'll just say a couple things here. So to make this reaction happen, it's using this uranium reaction that we saw on the previous page, this U-235, so I'll just go to the bottom of the page here. This U-235 fission reaction. This is the reaction happening in our nuclear reactors. And you see we need neutrons. We need the neutrons to smack into our uraniums. And in Candu reactors, what we do is called neutron moderation, which is where the neutrons are slowed down by heavy water. And you'll remember I mentioned heavy water a couple lessons ago as well. So they're slowed down by heavy water for the chain reaction. Because the slower those neutrons go, the more likely they are to smack into the uranium and cause a chain reaction. So they need to be slowed down. And that's one of the special things about the Candu reactors that other reactors don't do. So in other reactors, they need to use instead fuel that is a lot more radioactive, a lot more likely to split apart, just so that they can get around the fact that it doesn't happen as often. The Candu reactors uses natural uranium. So this is natural uranium here, which is just mined straight from the Earth, and it's 99.27% U-238, which is it's not fuel, it's not radioactive, and only 0.72% of that is U-235, which is radioactive. So the fuel that's used in Canadian Candu reactors is only less than 1% radioactive. You can actually take one of these fuel cells and hold it in your hand, and it's completely safe. It's not actually dangerous. And again, this is a way that Canada's reactors are different from the American reactors, is that the American reactors, they use enriched uranium, enriched plutonium that are a lot less stable and a lot less safe. Okay, so that's how Candu reactors work. Two more little points here about reactors in general. Radiation badges. These are little things that people working in nuclear reactors wear. And so you wear them, and they show how much radiation you've been exposed to. And so the idea is, of course, that you want those to always indicate that you haven't been exposed to much radiation, and the workers will check those to make sure that they're being safe. And if they start being exposed to too much, then they know they need to go into emergency protocol, that sort of thing. So that's a bit about the safety there. And the last thing is about waste disposal here. Well, nuclear reactors have very little pollution compared to coal and that sort of thing. But our nuclear or our radioactive waste needs to be stored safely for hundreds of years. So that's one downside of nuclear reactors in general. Okay, that's the end of the lesson. I hope you found it interesting. I think this is a pretty cool topic. So enjoy it. We'll see you in the next one.